Hi, my name is Andrei. I'm a researcher at the University of Manchester. And in this video, I want to discuss flexibility of distribution networks. How this flexibility can be aggregated from multiple renewable and distributed energy resources, and why understanding the limits of aggregated flexibility is so important for distribution system operators. The topic of network flexibility is very broad. There are multiple aspects like the limits of flexibility, voltage issues, flexibility markets, peer-to-peer markets, and so on. So it's impossible to cover all of these aspects and features in one single video, and I plan to make a series of videos about flexibility. In these videos, we are going to consider pictures like this, and I will try to convince you that modeling and analyzing flexibility is not only useful and instructive, but also simply beautiful. Now, a few words about this research. I have been working on the topic of network flexibility for about 2 years with my team, and we produced a lot of results and simulations. We have several manuscripts, not all of them are published yet, and I believe that it's not possible to explain all of these results in the papers, and I feel that I want to share these results with a broader audience, giving more insights and clues about flexibility models. And this is the reason why I plan to make this series of videos. All figures that I'm about to show are very much original. They are produced with my own optimization models, and I hope that you would enjoy them. And also I hope that you will find this video and modeling advice useful. Maybe it will even motivate you to study flexibility of distribution networks. And yeah, as I say, I plan to make a series of videos on active distribution network flexibility. And this first video, which will be around 20 minutes, is more like an introductory video. We will discuss why flexibility is needed, how to model the limits of aggregated network flexibility. And after that, we'll move to more difficult topics like flexibility markets, some game theoretical models, and so on. Okay, before coming to the modeling part, let me discuss why flexibility is an important topic nowadays. First of all, you may see that there is a myriad of publications in top power system research journals about flexibility. You can find many papers with titles like flexibility markets, DER flexibility provision, DER means distributed energy resources, peer-to-peer electricity markets, battery storage flexibility, energy communities, and some other combinations of these words which essentially mean some flexible operation of networks and flexible resources. But this topic is not only trendy and important because of the amount of publications. It is also getting attention from the companies, and many companies are making their move and publish their research and strategies about network flexibility. And I can speak at least for the UK. In the UK, there are so many reports. I would say that each distribution network company published their own strategy about flexibility. Just to give you a few examples, I will put this on the screen. Ofgem produced a report about their flexibility vision, and then each and every distribution company produced their strategy. Sometimes they call this not like network flexibility, but they call it DSO. They want to say that they are moving from distribution network operation, DNO, to distribution system operation. And essentially, if you read such reports, you will see that by DSO, they mean flexible network operation, that they are going to use this flexibility in distribution networks. And as you may see on your screen, Scottish Power Energy Networks produced their DSO strategy. Western Power Distribution report called DNO Transition to DSO, Electricity Northwest, and so on and so forth. So at least in the UK, each company is claiming that they're going to develop in this direction of flexible active distribution networks. So we can see that flexible distribution networks attract attention from both academia and industry, and this is why it is a very important and trendy topic nowadays. This is why I suggest you to study it. All right, let's begin. Before considering some cases, let's just consider a very simple network and discuss what is happening with its operation. As you can see, this is a simple network with 3 substations and 3 static loads, and we can say that this network is probably not flexible. But what do we mean by flexible and not flexible? Why do we call networks like this? So if network can change its regime, it can change its operating point, its consumption and energy generation, we usually say that this network is flexible. Sometimes in the literature, we call such networks active distribution networks. But as I said, in this simple example, this network has only 3 static loads and it cannot really change much its operation. Yes, we have a transformer at the primary substation, so we can change voltages a little bit, but still we cannot deviate much from the original operating point. How to describe this? Flexible network or not flexible? Well, we can plot the aggregated power consumption of the network in the PQ coordinates, that is, in the coordinates of active and reactive power consumption. And if we do this for such network, we will see a picture like this. You may notice that this is just a single point shown by this cross marker, and this is the only point that the network can operate in. This is why it's not flexible. So the only thing that this network does is it is just supplying the power demand, and it cannot change its operation. This is why we say it's not flexible. Well, let's consider a slightly modified version of this network. Let's consider a network which has some flexible units. For example, battery energy storage systems, DER like solar panels, electric vehicles that also have batteries inside and they also can change their power production or consumption. And if we can control these new elements installed in the network becomes flexible because it can actively change its power consumption and production. What is the set of feasible operating points for this new network with flexible resources? Well, this depends on the individual PQ capabilities of these units. And this is very case specific, but I can show you a picture from one of our studies which looks like this. And you can see this blue area here with this peculiar shape. The first thing that is important is that the operation of this network is not a single point anymore. We can change regimes of the network, we can deviate, we can shift our power consumption, both active and reactive power. This picture, the boundary of the aggregated network flexibility, provides a lot of information about network operation and its constraints. Since we consider the aggregated consumption of the network, this model also reflects all constraints that exist in the network, even somewhere deep in the network. And this is why this information could be so important for distribution system operators. And one thing that I want to mention here is the terminology, because different papers call these areas differently. You may find some terms like PQ feasibility areas or PQ flexibility areas, but there are some papers that always call these the boundaries of aggregated flexibility, these pictures, they always call it nodal operating envelopes. And which also makes sense because this is kind of an envelope of feasible operating points, nodal operating envelope. What information is shown in this picture? Well, for example, we can see by how much can we change network operation, by how much can we reduce its power consumption or increase it. And what is important here is that we cannot do this equally in all directions. For example, if we want to increase network aggregated consumption, both active and reactive power, P and Q, we can do this, of course, but we cannot do this infinitely. While we increase network consumption, we will face some constraints, probably voltage constraints or some kind of congestion. And we cannot increase it further because the operation will be infeasible. So we see the limits of increase. The same happens with the P and Q decrease. Once we start decreasing active and reactive power consumption, we will also meet some constraints, probably because of some voltage limitations. Maybe some solar panels cannot produce power anymore. So distribution system operators, by analyzing these limits, the boundary of the flexibility area, can know how to operate their network and where are the nearby limits of this operation. Estimating the limits of aggregated flexibility, finding nodal operating envelopes, pictures like this, answers many relevant questions about the operation of distribution networks. First of all, it shows how we can operate the network and how we can create coordination between transmission and distribution levels. So in this example, we considered aggregated power at the primary substation, but in some studies, this substation is called TSO-DSO interface. And we can see how we can trade this aggregated flexibility between distribution system and transmission system. Then we can identify some voltage issues and congestions and use these areas to develop markets for flexibility energy and even consider some investment models. For example, in some studies, we can produce these flexibility areas to see how much we can change our network demand and use this to defer investments in the network. So instead of building new cables right here and right now, we can use this possible, feasible, flexible operating area and understand that there is no need to install new cables right now. We can defer these investments and use flexibility resources instead. So understanding the limits of aggregated flexibility is very important for distribution system operators. But the question is, how exactly do we estimate, how can we compute these boundaries of flexibility areas? And there exist several approaches in the literature. There is a simplified, straightforward approach, which is called the Minkowski addition. You can Google, this is a very interesting concept. There is a good article on Wikipedia about the Minkowski addition. And the definition is that the addition of two sets, let's say A and B, is another set that is formed by the summation of any vector in A plus any vector in B. As you can see in this picture, the Minkowski addition of set A and B becomes a new set which is much larger than the original sets. And this shows how flexibility really works. When we have multiple units, they have different flexibilities, but the aggregated flexibility provides much more opportunities for the distribution system operation. The problem with the Minkowski addition is that it doesn't consider any network constraints. So this is just a mathematical term, how we can operate several sets, but no network constraints, no real power transmission physics is included here. That's why we need to use other models. And the general approach in the literature is to use some iterative OPF models. OPF means optimal power flow. And to explain this, I created this small fancy visualization, how by solving a number of optimal power flows, we can reconstruct and approximate the aggregated flexibility area. I don't want to discuss the equations and power flow models in detail here. So if you are interested in the equations, please check the manuscripts. I will put all the links in the description. The main thing here to discuss is the idea, how we can approximate the aggregated flexibility area by iteratively solving a number of optimal power flow problems. In my research, I use quite a simple and straightforward approach, which is called an absolute constraint method. The idea is very simple. We need to find the extreme points of this aggregated flexibility area. For example, we can start with the reactive power consumption maximum, Qmax, and then minimum, Qmin. Well, we know these 2 points, as you may see in the simulation, and then we start creating more points between them. So we start creating intervals with the desired accuracy, or sometimes it's called desired granularity. And for this case, I think there is like 20 intervals, and we start increasing, we start making steps from Qmin towards Qmax. And in each step, we find 2 more points corresponding to P maximum and P minimum. I mean that at this step, Q is fixed, and we find 2 P points. And then we repeat, we go up, we find another Q interval, we fix Q, we fix reactive power, and we start finding active minimum consumption and active power maximum consumption. The only thing is that once we finish with these Q intervals, we can see that there are some points which have a lot of space between them. So this approximation could be not very accurate. So what I do, I repeat this iterative process. Now for P intervals, I find active power minimum, P minimum, and then active power maximum, P maximum. And I create intervals between them. And within these intervals, I find Q points, Q minimum, Q maximum. And you see that with these 2 loops, 2 iterative processes, we very much accurately reconstruct, approximate the aggregated flexibility area. How much flexible power can we provide at the primary substation or for the transmission network? What constraints we face, and how much flexibility in total can we use? So very efficient and very useful approach, creating the boundary of aggregated flexibility area. A few more words about this modeling process. I want to recommend you to use exact AC power flow models. You can select from a variety of formulations, for example, nonlinear ACOPF in polar voltage coordinates, nonlinear ACOPF in rectangular voltage coordinates, or some models like DISFlow OPF for radial distribution networks. In my research, I programmed all of these OPF formulations from scratch, but you don't have to do this. There are many libraries that you can use already. For example, in Julia programming, you can use Julia power models, in Python, Panda power, and in MATLAB, of course, very famous MATPower. And you don't have to create anything, you just have to create a few loops and solve optimal power flow in the loop to find the limits and the boundary of the aggregated flexibility that we discussed. And I want to warn you not to use DC power flow models or any relaxations and approximations, because eventually you will see different images, you will get different shapes, and sometimes they will be not correct. They could be not AC feasible, and basically you will overestimate the real flexibility that can be present in the network. So use any power flow models, but I recommend exact AC OPF formulations. So we discussed why the limits of the aggregated flexibility are so important. Let's talk a little bit about applications. In one of our manuscripts, we considered a real radial network and we placed 10 flexible units there. And well, when we compute the aggregated flexibility and we find this boundary, we can see what is the absolute maximum flexibility that the network can provide. But there is much more to it. For example, we can ask a question, how do we control these units and what is happening inside the flexibility area? What if we want to provide flexibility with activating a limited number of units? And in that study, we developed a mixed integer program where we limited the number of units activated and we produced a picture like this. So what you see here is basically a segmentation of the overall aggregated flexibility area of the network. And the white-black color scheme shows how many units are activated here. So the white segment in the center is the segment where we use only one unit at maximum. Then once we move forward from the initial operating point in the center, we can use regulations from 2 units, 3 units, 4, and so on. And of course, if we want to get the overall maximum aggregated flexibility, we need to deploy all 10 flexible units that are placed in the network. So this picture is interesting because it shows that there are multiple levels within the aggregated flexibility. A distribution system operator can be interested not only in one boundary, like what is the absolute maximum of aggregate flexibility, but there could be many relevant questions like how to operate these units, how to control them. But there is another more interesting question here about the reliability of flexibility services provision. How reliable is the operation of the network and how reliable is activation of several units together if we want to produce a certain service? To analyze that, in the same paper, we assigned reliability coefficients to each unit. The coefficients are quite good, so each unit has a reliability of about 0.95 to 0.99. So each unit is quite reliable. But then, if you want to produce this aggregated flexibility, you need to activate eventually all of them. And if you multiply these reliabilities, you get a much lower one, something like 0.75. And we produced the following aggregated flexibility segmentation. And this segmentation is much more complex. It shows not the number of units that we need to activate, but the corresponding reliability. And the white-red color scheme here shows the level of the overall service reliability, which goes from almost 0.99 down to 0.75. And the further we go from the initial operating point, we need to activate more and more flexible units, and their joint reliability goes down dramatically. So this concept of flexibility area segmentation based on reliability gives much more information to the system operator. Now it knows not only how many units need to be activated, but also is that flexibility service reliable or not? We see different levels of reliability in this map, but a system operator can have some standards. For example, it might want to provide services with reliability more than 90%, more than 0.9. In this case, we just constrain the subset of these areas that have resulting reliabilities more than 0.9. And we get this sub area shown here on the picture by a dashed line. And we see that this, we can say, more reliable area, more reliable region is much smaller than the overall aggregate flexibility area, which is an interesting outcome, that if we want to include some reliability analysis in this aggregated flexibility, we get the areas shrinked and decreased dramatically. I want to mention that this is a very simple model that we use in the paper. We just assigned some coefficients to each flexible unit, and we didn't perform any stochastic and robust analysis. So I think there is more research needed for this topic to analyze reliability-based segmentation of aggregate flexibility areas. I think that's all for the introductory video. We discussed why the aggregated flexibility is important for distribution system operators. We discussed these models for approximating the PQ flexibility areas. In the next videos, we will consider much more complex concepts. We will apply game theoretic and cost minimization models to flexibility provision at each feasible operating point within these areas. So there will be a lot of interesting and beautiful pictures coming. And I plan to film the next video shortly and hope to see you there soon. Bye.